Last week, we focused on the numerical solution or computational solution of ordinary differential equations. So the kind of method for figuring out the solution, the approach numerically to figuring out the solution. We talked about the Euler method for solving ordinary differential equations. That's based on the sort of lowest level Taylor series approximation for a function. We talked about Runge-Kudde methods for solving ordinary differential equations. They use higher order Taylor approximations for solving numerically the ordinary differential equations. We talked about errors and uncertainties and approximations. So we talked about specifically approximation errors, which are related to the approximations we make with the Taylor expansion. And we talked about truncation errors, which are errors that are made when we use floating point numbers on computers and limit the number of digits for floating point numbers on computers. We looked at applications of methods, procedures for solving ordinary differential equations to falling bodies. The solutions there are polynomials. We looked at exponential growth, exponential decay, where we've got exponential solutions. And then we looked at the case of differential equations with solutions that have periodic structure to them, sinusoidal structure to them. So we walked through kind of the world of ordinary differential equations, the simpler ones. Today's class and the next class, I want to work on a particular problem, a very specific problem, pendulum motion. We're going to look at simple pendulum motion. We're going to look at damped pendulum motion. We're going to look at damp-driven pendulum motion. So we're going to explore this world quite extensively. There are cases here where the ordinary differential equations corresponding to the damp-driven pendulum can be solved analytically, but there are many cases where the problem of the damp-driven pendulum can't be solved analytically. So that's the virtue of the numerical techniques. We'll look at the effects of nonlinearity in the corresponding differential equation for the damp-driven pendulum, non-isochronicity, I can never say that word. We'll look at that for the damp-driven pendulum, and we'll look at, in the next class, the onset of chaos through bifurcation. So we're really going to explore this particular problem in quite a bit of detail, the damp-driven pendulum in quite a bit of detail. A few words about the pendulum, why we might be interested in it, and a little bit of history on it. Why we might be intrigued by it was the pendulum was key to, going back hundreds of years now, exploring the shape of the Earth. So pendulum was used for that. Exploring the Earth's rotation, pendulum was using that. And for the timekeeping that was needed for navigation and for exploration. So pendulum has been historically very, very important. The work on the pendulum's regularity, that the period is independent of the amplitude. That work was first done, as you know, by Galileo, and we get taught that in high school. The realization that the pendulum's motion actually, it doesn't have a regular period, a constant period for large amplitude oscillations. So that's the irregularity of the pendulum. That was work that was first done by Huygens, and we don't hear about that in high school. So we'll look at both those cases. We'll look at where the pendulum's period is constant for low amplitude oscillations of the pendulum, and where the pendulum period is not constant for higher amplitude oscillations of the pendulum. And that's a transition from a world of a nonlinear differential equation, a linear differential equation to a nonlinear differential equation. We'll move on to this case of the damped driven pendulum. That's where in the pendulum's motion, in addition to a restoring force that's causing the oscillations, there's a drag force, viscous force, that's impeding the oscillations. And then there's a driving force, a push-pull that's exerted on the pendulum, that's influencing the pendulum's motion. So all those three things are being involved. This is the case where there are special circumstances where you can solve that problem analytically, but in general, you can only solve it numerically. This is the case where we're really going to explore the nonlinearity of the ordinary differential equation describing the damp-driven pendulum. It's like the classic example of nonlinearity. It's for a damp-driven pendulum. It's partly because it's a case that is amenable to experiments on a damp-driven pendulum, so you can measure nonlinear effects, and also is very amenable to computation, numerical computation of nonlinear effects. We'll focus more on that next class when we talk about bifurcation and chaos. Okay, that's the plan. This is just a reminder of what we learned in high school about the pendulum. This is kind of a simple pendulum, an ideal pendulum. So just as a reminder, we've got a pivot at the top. We've got a string here from left to right. We've got some mass here that swings to and fro. And the idealizations that we make, that we're going to strip away one by one, that we're going to remove one by one, is starting at the top, that the pendulum swings in a frictionless manner. There's no drag forces, there's no viscous forces. We're going to remove that approximation. The string is rigid and it is massless. We can remove that approximation numerically, straightforwardly. The mass is idealized as a point mass. We can always remove that, eliminate that straightforwardly, numerically. The point is with the pendulum is that a component of gravity, the component that's not balanced by the tension in the string, that unbalanced component of the gravitational force is providing a restoring force that is always acting towards the equilibrium, the vertical position of the pendulum. So it's always pushing the pendulum back towards the equilibrium, whether it's on the left or on the right. It pushes back stronger the further you displace the pendulum from the equilibrium. It pushes back less when you're close to the equilibrium. And that restoring force is what generates the oscillating sinusoidal motion for a simple pendulum. I got 3 slides. I'm going to walk through the simple pendulum differential equation, ordinary differential equation, because we're going to be solving that. The damped pendulum, ordinary differential equation, because we're going to be solving that. And then thirdly, the damp-driven pendulum, its ordinary differential equation, because we're going to be solving that also. All of those 3 things in today's class. So this is just to introduce the 3 differential equations for undamped pendulum, damp-driven pendulum. Just introduce kind of the language and the parameters that we're going to use, and some of the main features of undamped, damped, and damp-driven pendulum. So this is the case of the simple pendulum. If you as I say, the restoring force, when you displace the pendulum from the vertical, from the equilibrium, acts to return the pendulum to the equilibrium, and it causes this oscillating motion of the pendulum. And we can think of it mathematically as arising from this differential equation here. So this is just the equation that arises if you equate the gravitational restoring force, that mg sine theta, with, if you plug that into Newton's second law, that is the equation of motion, F equals ma, and you write it in terms of theta, the angle of the pendulum, and its angular acceleration, that's the second order differential here. It's this little differential equation here. So that's a very simple to write down differential equation. It's actually a nonlinear differential equation. It's linear in this different second order differential here. It's not linear in the variable theta here. So this is a nonlinear differential equation. And often when we think about solutions to it, when we think about solving it, we think about a special case of this nonlinear differential equation for the pendulum. That's when theta is small, the angle theta is small. That's when sine theta is approximately theta, and that's this linear differential equation here. So now we're linear in the second order differential with respect to theta, and we're linear in the dependent variable theta itself. But this is the equation that has the kind of elegant sinusoidal solutions to it. Those solutions have a characteristic frequency to it. So a given pendulum in a given gravity field has a given as a characteristic or a natural frequency to it. That's just the square root of the acceleration of gravity divided by the length of the pendulum. So that comes out of this factor here. In this solution here, of course, you can have all sorts of amplitudes for your pendulum motion. You could have different phases for your pendulum motion. Those are parameters in the general solution that are determined by the initial conditions that you release the pendulum with. So the initial angle that you release it from, the initial angular velocity that you release it with. So those determine the amplitude and the phase. So one important point about this, which was, Galileo's finding, is that these solutions here have the special feature that the period or the frequency is independent of the amplitude, and it's independent of the mass of the pendulum. So it just depends on the length of the pendulum and depends on the acceleration of gravity. But it doesn't depend on the mass, and doesn't depend on the amplitude that you swing. As long as you stay in this regime where the swings are small in amplitude, where the equation, differential equation is linear. This is exactly the same equation that you're working with, differential equation that you were working with in the last homework from last week. We had a mass on a spring. It's the same form for the differential equation. It's just a form in which instead of the coefficient between the second order differential and the dependent function itself was the ratio of the mass of the object to the spring constant of the spring. Now that coefficient is the ratio of the acceleration of gravity to the length of the string. But it was exactly the same differential equation. Now let's add on damping. So I just, in the figure, add a drag force. We met drag forces in projectile motion, in falling body motion that oppose the motion of the body through the fluid like air or water. So I've added a drag force opposing the motion here. The drag force that I've sketched here is a linear drag force. We also talked about quadratic drag forces. In falling bodies, there are analytical solutions for linear drag forces and quadratic drag forces. In the case of the pendulum, there's an analytical solution for the linear drag force, but I don't think there's an analytical solution for the quadratic drag force. So on this sketch here, and in these equations here, I'm using a linear drag force. We would have to use the linear drag force for an analytical solution. But if we wanted to do a quadratic drag force and a numerical solution, that would be fine too. So going upstairs here, I've added, in addition to the differential equation we built out of the law of motion and the force of gravity, a additional term here is the drag force. In talking about projectiles, we wrote the drag force in the linear drag force as a coefficient of drag v times a velocity v. Here we're describing the pendulum not in terms of its position and its velocity and its acceleration, but rather in terms of its angle, its angular velocity, its angular acceleration. So I'm using, theta prime rather than v. But I've also changed from the lowercase b to a beta. Those two are related to one another. I wrote it down here. 2 beta is b over m. B over m is what we were familiar with from the from the falling bodies. Beta is what's traditionally used for the pendulum, just because it's sort of more convenient. The solutions are simpler in the language of beta than they are in the language of lowercase b. So we'll use this beta here. It's just a coefficient of drag again. Again, this is a non-linear differential equation. It is linear in the second order differential, theta double prime. It's linear in the first order differential of the dependent variable, theta prime, but it's not linear in the dependent variable set because it's sine theta. So that's non-linear. However, again, in the case of small angle displacement, where you can apply the small angle approximation, where sine theta is approximately equal to theta, then we have this small angle damped pendulum ordinary differential equation, which is linear. So this is linear in theta and it's first and second order differential. So this is a linear differential equation that can be solved analytically. There's some interesting features. There's 3, we mentioned this before when introducing, I think when we were doing if else and else statements. We said that there is a discriminant in the solution to this differential equation that discriminates between either periodic oscillating motion, damped oscillating motion, or non-periodic, just exponential decaying motion. So this is the discriminant that discriminates between these different regimes of motion, the solutions of this equation. When you get under damping, it means that beta is smaller than this natural frequency of the pendulum. And when you get, and that gives you oscillating solutions. When you get over damping or critical damping, so beta is greater than equal to the natural frequency, that's when you lose the oscillating behavior. Here's the solution for the underdamping case. Interesting to compare it to the solution for the no damping case. You, in both cases, got sinusoidal oscillations. In the zero damping case, there was a single natural frequency. In the underdamping case, this frequency varies with the relative sizes of the natural frequency and the damping constant. So this doesn't exhibit a constant period with the damping constant. The frequency omega d, I thought, it depends on the damping constant. So already we've lost, by just damping the pendulum, even at small amplitudes for the pendulum's motion, we've lost this feature of a period that's independent of amplitude. What else can I say about it? Well, it's not only oscillating, but it's damped oscillations. That's what the exponent negative exponent does here, and the damping is greater for larger beta, smaller for smaller beta. Okay, we'll explore all these features in our calculation. This is the last review slide. This is damp-driven pendulum. So common situations with pendulum are applying a driving force. Mechanical situations also often involve applying a driving force. A common situation is, pushing a child on a swing or something like that. That's a drive. You're pushing a driving force. So I pictured the driving force here, little arrow here, because you could, push against the motion or push with the motion. I pictured the driving force. Actually, I pictured a special case. This is an important case of a driving force where the driving force it's not just a constant driving force. There's actually a sinusoidal driving force. That's a very practical, important case. So if you apply a sinusoidal driving force, it has a certain strength to it. So that's the force there. And it would sinusoidal drive force, it will have a certain frequency for the application of the driving force. And because general, it's not the natural frequency. So I thought that omega n. So these are the two parameters that you introduce with the driving force. I wrote down the differential equation for it here. Now we're getting a bit more complicated. We got, again, it's built out of equations of motion. The angular acceleration, that's the left-hand side here, the second order differential of theta, is determined by three terms now. There's one arising from the gravitational restoring force, one arising from the drag or viscous force with this parameter beta, that is the drag coefficient, and then one arising from the driving force here. And I'd introduce another coefficient here. This is what we might call the driving constant. The driving constant I'm just defining as the ratio of the applied force, the driving force, to the gravitational force, total gravitational force mg. So this again is a kind of a convenience for us to introduce this gamma here. I'll work in terms of this gamma. So again, this is non-linear. It's linear in the second order differential, linear in the first order differential. This doesn't involve the dependent function, so that's fine in a linear differential equation to add a term like that. But the non-linearity occurs due to the sine beta here. So again, we can think of a special case where the theta is small, the sine theta is approximately theta, the small angle approximation is this equation here. So this is a linear version of that equation. The solutions to that equation generally involve an interesting feature where you look at the solution with some initial conditions. You kind of see a transient period where things are changing in a relatively complicated way. And then after the transient period, what you'd often see is that the object just oscillates simply sinusoidally with the driving frequency. The transient period, more complicated motion, in that you can see both the natural frequency of the pendulum and the driving frequency, the driving force. But once you get to steady state, you typically see just the driving frequency, not the natural frequency in the sinusoidal solutions. So that's one class of solutions to this that is amenable to analytical and numerical calculation. This is the class where there's this, the famous effect of resonance. If the driving frequency is far from the natural frequency of the pendulum, then the oscillations at steady state that have the driving frequency are going to be small. If the driving frequency is close to the natural frequency, then the oscillations at steady state are going to be large, and that's resonance, and that's a very important effect in physics and in engineering too. And this is just the equation for that amplitude that tells us, you know, whether the amplitude is going to be large or small, whether depending on whether we're close or far from resonance. So it amounts to the comparison of these two frequencies, the natural frequency of the pendulum and the frequency of the driving force. And if they're close to one another, that makes the denominator small, so the amplitude becomes big, and vice versa. Okay. Let's move on. I put this in here because I kind of like the figure, but Huygens was famous for understanding, firstly, that the pendulum motion wasn't independent of
my laptop's about to die. Do you mind if I plug my laptop over?
Yeah, if you can find a spot to plug it, it's fine. Huygens was famous for figuring out that the pendulum's motion and its intensity of the period or the frequency to the amplitude of the motion was independent of amplitude. Figuring out for large amplitude motion, that's not true. The period of the pendulum and the frequency of the pendulum does depend on the time. So he was famous for that. He was also famous for developing a clock, a pendulum clock, that would handle the damping effects, which dissipate energy from the clock and change the frequency. He was able to introduce energy with a driving force to counteract the loss of energy from the damping force, and therefore maintain the frequency of the constant frequency of the pendulum. So if you have a pendulum clock and there is a damping force, that will change the frequency of the pendulum clock. If you introduce a driving force to kind of replenish the lost energy, you can maintain the constant frequency of the pendulum clock. And that, that's very important achievement in terms of it reaching stable, long-term stable clocks. Okay. Few words on linear versus nonlinear ordinary differential equations. So just to be very specific, very clear, when we say that a differential equation is a linear differential equation, what we mean is that the dependent variable in the equation, so this is the theta in the equations for the pendulum here, and its differentials. We've got a first order and a second order differential in equations we've been talking about. They only appear linearly in the differential equation. If we've got a theta in our ordinary differential equation, and we got a theta prime, and we got a theta double prime, if they're just appearing linearly in the differential equation, that's a linear differential equation. If they don't appear linearly, now in our cases, theta double prime appeared linearly. Theta prime appeared linearly, but we had the sine of theta appearing, which is a non-linear appearance of the dependent variable theta, then that's a non-linear differential equation. So that's the first point that I would want to make. So what makes the damp-driven pendulum non-linear is the restoring force that we're introducing in the case of the linear damping. So it's the restoring force, the first thing that we introduce that makes it non-linear, and it's the sine theta term that makes it non-linear, distinguishes between the non-linear and linear cases of it. As I say, for the linear case, if you just have simple undamped oscillations, the frequency is independent of the amplitude, but for the non-linear case, it is dependent on the amplitude. Not only that, right? In the take the simple pendulum, small amplitude oscillations. The oscillations are perfectly sinusoidal, so they have just one distinct frequency associated with them. If you make the amplitude of the oscillations large for the simple pendulum, the oscillations are not sinusoidal, they are periodic, but they're actually superpositions of sinusoidal oscillations, of harmonics of the natural frequency. So the nonlinear pendulum, without damping, without driving forces, for large amplitudes is periodic but non-sinusoidal. It's only periodic and sinusoidal when the amplitude of the oscillations are small. And it's these non-linearities that cause the ultimately the cause of the chaotic effects and bifurcation on the way to chaotic effects. Okay. So I want to say about how I'm going to code up the damp-driven pendulum. And I'm going to code up the damp-driven pendulum in the way that we discussed last week for second-order differential equations, because this is an example of a second-order differential equation. So I just wanted to walk through this as a reminder of how we coded up second-order differential equations. So here's upstairs, this first bullet is just a remark about general second-order differential equations. Upstairs is the form of it. Remember, a second-order differential equation has a general form, but the second-order differential of the dependent variable is equal to some function of the dependent variable, the first-order differential of the dependent variable, and the independent variable denoted as time here. So in our case, right, of the pendulum motion, the second order differential of the dependent variable is theta double prime, the angular acceleration, and the general equation could depend on some function of the dependent variable theta is differential theta prime and the time variable, the dependent variable. When we go ahead and solve that numerically, what we do is we decompose the second order differential equation into two first order differential equations by introducing a new variable that has some physical significance. We define a new variable is the first order differential of the dependent function. So the dependent function upstairs here is y. We're going to define a new variable that now call it v for velocity, which is the first order differential of y. And we're going to write down two differential equations, one for the original variable y, so one that says y prime equals, and the second one for the new variable v, the second one saying what v prime equals. Well, for the one for saying what y prime is equal to, it's just the definition of v. This is just how we define the new variable. And the one that says what the differential of the new variable is well, if y prime is equal to v, then y double prime is going to be equal to v prime. And so it's just that differential equation that was equal to y, we wrote equal to y double prime, but it's also equal to v prime. And so this is a decomposition of the second order differential into two first order differential equations. And I'm going to write them in the computer in this fashion. I'm going to use this meta variable two element vector to specify both y and v. say the position and the velocity, and I'm going to use that meta variable again in a two-component form to specify the two differential equations. So I'll have two differential equations that kind of form the two elements of this this meta differential equation. This is how I'm going to do it in the code. So this is now, I want to code up my damp-driven pendulum differential equation. So I want to code up this thing here. I should have put this in terms of the damping constant. Put it here in terms of the damping constant. So now that the two variables for our two first order differential equations are the original variable theta and the angular velocity, which is equal to theta prime. So these are the two variables. There are two corresponding differential equations. The upper row here is that we defined omega as theta prime. So that's the first row. And then the second one is that omega prime, which is theta double prime, is equal to the right-hand side of that differential equation. So this is how we're going to code up the two variables of our first order differential equations and the differentials themselves. So once we've done that, once we've specified the initial values of theta I, the values of theta and omega at a certain time, say theta I, omega I, then we can just propagate them to the next time, theta I plus 1, omega I plus 1, by using the Taylor expansion, effectively, by using Euler code that we developed in the last Tuesday's class, or the Runge-Kutta codes that we developed in last Thursday's classes. So that's basically the plan, and build, sort of extrapolate or construct outwards the solutions to the differential equation from some starting initial conditions for theta and omega. I call them theta naught and omega naught here. Okay. Any questions on that? I'm going to go on to the code that I wrote for it. So any questions? Yeah.
We will be doing large amplitudes, right?
So yes, we will be doing large amplitude, and we're going to do large amplitude a little bit in this class. And so we'll see the effects of doing that, the nonlinear differential equation. We'll do it more in the next one.
Okay.
We're going to actually spend a few classes working on this, because there's a lot of different, spaces or regimes in the solutions to this. There's also a lot of different approaches to visualizing and plotting the damp-driven pendulum. So we'll spend some time on that. Okay, so I added I got now a RK4 damp-driven pendulum notebook in my physics 508 directory. I put that in there. So the first cell is where I define my user functions that are going to help me solve the pendulum second order differential equation. I import some other package functions that I'm going to use. I'm going to import from NumPy, and I'm going to import from Matplotlib for the arrays and the plotting I need. I also define the time space, this discrete time world that I'm going to work in this first cell. So I'm basically setting up the world in which I'm going to do my calculation. And then it'll be the next cell that I'll do my calculation. I've got to make this bigger. I realize that. Nobody can read it. Okay, so maybe I'll just walk through this. Don't worry about this. I have a cell that's below these cells where I try to make a plot of the pendulum swinging backwards and forwards, no, I did make a plot pendulum swinging backwards and forwards, but I didn't use it for this. I used this if I wanted driving forces that are non-sinusoidal. That package had lots of functions in where I could have a square wave function rather than a sinusoidal function, or a trapezoid function rather than sinusoidal functions. So I used it for that. Actually, now I'm remembering, but I'm not going to use it for that right now. So it may as well not be that. We talked about this the last class. This is my user function that calculates the future position and velocity, or angular position and angular velocity of the pendulum based on the current angle and angular velocity of the pendulum using the Runge-Kutta method. Remember, this is a method that uses the Taylor expansion and should be good on individual steps to the fourth power in that little time interval dt from one tick to the next tick. It does so by making 4 separate estimates of the slope of the function, the differential of the function, across a time tick, and using those 4 estimates, estimate the function's value at the end of the tick, knowing the function's values at the beginning of the tick. So it's sort of a very accepted compromise between making a precision estimate of the function a tick later and not having an overly complicated estimate of the function a tick later. Okay, so we've met that before, and I just cut and paste this from last week's. Last week we also had a function that defined a differential. So in the case of a first order differential equation, then there was just one that we were solving. There was just one first order differential equation. Now we're solving a second order differential equation. There's 2 first order differential equations that are coded up in this user function. So my user function is called pendulum. I'm passing to it the current values of the coordinates of the pendulum, and it's going to return the future values of the differentials of those. Sorry, it's going to return the differentials of the coordinates. So the important point here is that when I pass y here, which gets passed from the Euler function, this is going to be 2-component, 2-element vector. That's the meta variable that contains the angle of the pendulum and the angular velocity of the pendulum. So this has 2 elements, and those 2 elements you can reference individually by y of 0, that's the 0th element, and y of 1. So it's a 2-element vector with a position and velocity coordinates that we use separately when we define the differential equations. And what were the differential equations for the pendulum? One of them was just that d theta by dt, the first differential theta, is equal to omega, the velocity that we introduced. That's all I'm specifying here. That's the first differential equation. And then the second differential equation, and I'm specifying in these 3 lines here. And it's just a choice to split it into 3 lines. This is the differential equation where we say that that variable that we introduced, omega prime equals, these terms in the differential equation that correspond to restoring, damping, and driving forces. And I just add them in one by one. So this first line just defines the differential as G over L times sine theta. So that's the term that you would get for just a simple pendulum. And that's the term that would approximate to G over L times theta if it was small amplitude oscillation. So that's the restoring force. And then I'm gonna add in, but there's a, because it opposes the motion, there's a minus sign here. I'm gonna add in the damping force. Remember in the equation that appeared, we used this quantity beta as a damping constant, and it appeared as -2 beta times the velocity, angular velocity of the pendulum. So here I've got -2 beta times y1, remember, is the angular velocity of the pendulum. So that's the damping, the effects of the damping force. And then I've got the driving force down here. The driving force, its strength was characterized by a driving constant. I called it gamma. It's basically the ratio. It is the ratio between the amplitude of the driving force and the force of gravity on the object. So that's the gamma here. Its sinusoidal dependence was characterized by its own frequency. That's the omega f here. And I add that force on. So at this point, if you call this function, you call it with these this variable that has two elements. Those two elements define the differentials of each of those elements by these equations here. And then I return another two-element object and constructing it here out of the differentials that are in these two equations here, and I return that. So it calls with the values of theta and omega, and it returns with the differentials of theta and omega. And that's what all this function does. And that's all the Euler method needs, or the Runge-Kutta methods need. The Runge-Kutta method that we're using here. That's just what it needs. It just needs to ask this function, given this value of theta, this value of angular velocity omega, what is the differential, numerical value of the differential of theta and omega. So we return that here. This is, I was kind of playing around, as I mentioned, with driving force functions that are non-sinusoidal. This is one of the great things about numerical solutions. It's very easy to do that. So right now in my differential equation, I got a sinusoidal function, but it would be easy to replace this sinusoidal driving force with a square wave driving force. There's a function for that defined in the SciPy library. So that's why I grabbed that. A sawtooth driving force is a function for that in the SciPy library. So I grabbed it here, or any other sort of driving force that I could invent. So anyway, just to let you know. Obviously, the other really important ingredient is that we're working not in continuous time, but discrete time. So I've got to define my discrete time. I chose to have 2000 steps of time. I chose the range of the time, I called it tau, to be 20 seconds. And then based on that, I calculated the time between the individual ticks. Obviously, it's going to be 10 milliseconds, hundredth of a second. So that's the dt here. And once I define those parameters that describe my discrete time, I define this kind of proxy for a continuous variable time. That's a finely spaced series of ticks in time. So this is a 2000 element array containing all the ticks of time that I'm going to walk through in my ordinary differential equation calculation, once I define that independent variable, I define the two, I define the dependent variables through this theta here. So theta has, think of it as it's a matrix with two columns to it, which are all the individual times of the ticks. The first column is going to be the position variable, the theta coordinate, and the second column is going to be the angular velocity variable, the omega coordinate. So this variable theta, meta variable theta, contains both theta and omega, because it's a 2 by n matrix, which are the dependent variables corresponding to this time variable t. The last line, that was, it's not related to the numerical solution of the ordinary differential equation. The last line is I just wanted to compare my numerical solution of the ordinary differential equation to just simple sinusoidal motion calculated with the analytical formula, the sinusoidal motion. So this is going to be it's an n by 2 array. It's going to contain omega and theta for all the times of my dependent variable t, but the values are just going to be a case of simple pendulum motion as kind of a reference point for effects like damping or driving or whatever. Okay. So now this next cell, make it a little bit smaller. Okay, I can get the whole thing, all the calculation on one screen. This is the entire calculation in this one cell here. This block upstairs here is just to define all the pendulum parameters that I need. So I define the acceleration of gravity, I define the length of the pendulum. Remember, those are the two things we said that would determine the natural frequency of the pendulum by this little equation here. The natural frequency is the square root of g over n. So that's my simple pendulum. Then to introduce the damping and the driving forces, I need to introduce the damping constant, the driving constant. I also need to, because they compare to the gravitational forces, I need to know the math that determines the gravitational force of the pendulum. So here I'm defining the mass of the pendulum, the beta for the damping force, the gamma for the driving constant, the driving frequency, that's the omega f. I define all those things that I need. I'll come back to why I wrote certain values in certain ways when we get to playing with the code. But anyway, I'm defining all these values I need. I've got to set the initial values for the pendulum swinging. So I've got to, there is no numerical solution, analytical solutions, without setting an initial value for theta and omega. If you don't do that, there's nothing in the numerical method. So I here set the initial value of theta and omega, theta naught, omega naught, 0.1 radians in this example here. So I'm displacing it by a handful of degrees from the equilibrium. I'm releasing it from rest. So omega naught is 0. And I'm setting the first element of the of theta times 0. I'm setting that variable theta to be theta naught, and the variable omega that's stored in that 2D array, it's at the first time interval, I'm going to set it to be omega naught. And then the whole calculation, ironically, comes down to this pair of lines here, right? A for loop over all the time intervals from the first one I'm starting at, where I initially know theta naught, omega naught. So for either all the remaining time intervals, in which I calculate the future value of theta from the current value of theta by calling the RK4 function, which includes the name of the differential equation we're solving. So this string here. So this is the core. It takes the current values of theta and omega, so theta I, omega I, and projections to the next clock tick, calculates theta I plus 1, omega I plus 1. And it just does that time and time again through all our little ticks in time. I wrote the indexing of theta, the current value, and the indexing of the future value, kind of a funny way, but I wanted to emphasize that. So this first index here represents the time. So we're at time, the current time is time tick J, and we're going to project the coordinates to time tick J plus 1. So that's important. The first element is the time tick, and we are projecting that from current time to the future time. Remember, when we defined theta, we defined it as an n by 2 array. So n represented the time, the 2 represented the two variables. So we're picking out one time here and then the following time here. And the second argument is referring, after the comma, is referring to the two elements, the pair of elements, the theta and the omega. And this slicing here with just a colon just says slice both elements out. So we're going to pass both theta and omega with this slicing here. And we're going to set both omega and theta for the later time with this slicing here. So that's the reason for that kind of funny structure in those arguments here. You don't actually, it will infer it if you took this out, right? And you took this out here. But if you take it out, that's fine in doing a calculation. That's perfectly fine in doing a calculation. But you might forget that this is a two-dimensional array. So I put it in there to remind me that it is a two-dimensional array. All the calculations done there. This last little calculation down here, which looks way more complicated, is just the calculating the analytical solution for simple harmonic motion for the given value of theta naught and the given value of omega naught. So that's just an analytical solution to compare with. And then I'm just going to plot two graphs. So there's two plots here. And make two subplots here. And one of them is the variable theta. I'm slicing out with this 0 here. I'm slicing out the theta for all times. This is sort of the reverse of the use of the colon and that I was discussing before. This colon here for the first index is selecting out all times, but just for the 0th element of the second index. So that gives you time. That gives you theta. This down here, by comparison, this is slicing out omega. So this is giving you all times, but for the dependent variable, but just the omega. And so this is going to be a plot of theta versus time in the first cell, So this is a plot of omega versus time in the second study. Obviously, then I label them with theta and omega. I compare them with that simple harmonic motion analytical calculation, where I've also stored a array that's n by 2, where I have to do the same sort of slicing to pick out the theta simple harmonic motion and the omega simple harmonic motion. Okay, so let's take a look at that. Well, look, I turned off the damping. I turned off the driving force. I set the amplitude of the oscillations to be small. The initial amplitude of the oscillations were the 10th of a radian, so 5 or 6 degrees, so small oscillations. I expect simple sinusoidal motion. And if we look at these plots here, the top one is theta as a function of time for 20 seconds. Bottom one is omega as a function of time for 20 seconds. And the blue points, which are kind of overlapping, and the red line, the blue points are the numerical, the red line is the analytical, and you see it just verified or reproduced the analytical solution. So that's a worthwhile test of our code to check that we can reproduce this this solution that's amenable to analytical approach. The period of these oscillations should run back up here. G was 9.8 meters per second squared, and the length of the pendulum was 1 meter. So G over L is 9.8. Square root of 9.8 is about 3.1. So the natural frequency, which is the square root of G over L, is going to be 3.1 radians per second. That means that to complete with a one period, which is completing 2 radians, will be 3.1 is just under pi. So it's just a frequency that's just under pi radians per second. The period will be just over, fractionally over 2 seconds, I think, for the pendulum. So let's double check that makes sense. And it looks like it is. So here's one period, which is 2 seconds. And the amplitude we started the oscillations with was 0.1 radian, and it just maintains that amplitude. There's no damping here. And the initial velocity was 0. So the graph here starts from 0. And the two plots are omega and theta are out of phase, because when omega is maximum at the equilibrium points, theta is 0, and vice versa. So that all makes sense. Let's do some things that are more interesting. Let's where have I going? I want to change the amplitude of the oscillations, because that was your question. Can we see nonlinear effects? So let's make this 1. Let's make this 10 times bigger. So now this is releasing not from 5 or 6 degrees, but from 57 degrees. Well, this is a big amplitude oscillation. So no longer can we make the approximation that sine theta is approximately theta if we start with theta naught of 57 degrees. And that's what you see here, right? Now we have the longer period for the oscillations. The period of the blue, which is the numerical calculation for this situation, is longer than the period of the red, which was the simple harmonic motion solution that assumes a linear differential equation. So that's one difference there. I think we made it larger still a bit. This there's 1.5 for the amplitude here. And I guess, again, you're seeing that you've got an even greater difference in the periods here than we had in the previous case. The curves, it's hard to see on here, but the curves are no longer perfectly sinusoidal for the numerical calculation. They are actually a superposition of the natural frequency and other harmonic. Okay, so that's looking at whether the frequency is independent of the amplitude, and it's not independent of the amplitude at large oscillations. Let's switch on damping. So I'm going to go back to 0.1 here. And we'll switch on damping. Now I wrote the damping this way. Using beta, the critical value of the critical damping will be when beta equals omega naught. Now omega naught is 3.13, the square root of G over L. And so I'm going to define my beta as a multiple of that natural frequency. If I define it as smaller than that natural frequency, so this would be critical, this would be under damping. If I made it 1, that would be over damping. If I made it 10, that would be, sorry, if I made it 1, that would be critical damping. If I make it 10, that's over damping. So let's check all that. Let's put 0.1. This is beta smaller than omega. And here's the results of our calculation. Again, now this is a use of the red plot. You see how it compares with simple undamped sinusoidal motion. The blue is our damped motion. You see that our damped motion exhibits, because it's underdamped, it exhibits sinusoidal motion, as we said it would. Its period, it's hard to see on here, but its period is a little bit longer than the period of the natural frequency period. The damping constant is causing this damping here, and the time scale for the damping is kind of the inverse of the damping constant. So it's about 10 seconds. So that's under damping. If we make this 1, this is critical damping. We make this number 1, beta 3.13. And remember, omega naught is 3.13, the natural frequency. So now they're the same, which is the condition of critical damping. Now you see we've lost the oscillations. Rather, the pendulum just swings back within a couple of seconds to the equilibrium point. If you look at the velocity, what's happening with the velocity here? Well, we just suddenly, the pendulum was out somewhere here, over here on the right. We've released it. It starts to accelerate back under gravity towards the equilibrium. But of course, the drag force is trying to impede that. So it speeds up to begin with, and it slows down towards the end as gravity gets smaller and comes to rest. So this is a kind of map of how gravity falls off with time as the pendulum swings back, a component of gravity, but the drag force depends on the velocity, will grow initially as the pendulum gets faster and faster. If I made the damping larger, so that's critical damping, no oscillations. If I made it 10, what's the effect of doing that? Well, here's 10. What you're seeing, the pendulum moves very, very slowly back towards the equilibrium point. So the pendulum slowly glides back towards the equilibrium point. The velocity of the pendulum, the angular velocity of the pendulum, is always very, very small. And so compared to critical damping, where the pendulum swung without oscillations quickly back to the equilibrium point, the difference for overdamping is, well, you've still got no oscillations. The pendulum swinging back to the equilibrium point, but it's much slower. So the importance of critical damping is you eliminate the displacement as fast as possible without oscillations. That's the importance of it. Okay, let's switch on a driving force. I think I'm going to put this back. I'm going to put this back to the underdamping case, point 1. And the reason I'm doing that is if I introduce a driving force, I'm going to be inputting energy. If I just input energy and don't have any way of dissipating energy, the oscillations are just going to grow and grow and grow and grow. So I'm going to kind of try and balance the input of energy through the injection of energy through the driving force and the release or dissipation of energy through the drag force by having both switched on now. I'm going to set gamma now to be non-zero. So this is the driving constant that is that we defined, which is the driving force divided by the gravitational force. So I'm going to set a value here of gamma based on a force of 0.1 newtons, which I got some notes that I made for myself, but I can't read them. So I think that's what I did. So now we've got a driving force, and I've got a frequency for that driving force. Look at the way I'm defining the frequency. I'm kind of like I did with the damping constant. I'm defining it in units, the driving frequency in units of the natural frequency. So I'm going to use a driving frequency that is 5 times the natural frequency. So a period that is 1/5 of the natural period. But let's do that. So that would be relatively far, quite away from resonance, right? Because I've got a driving frequency is 5 times the natural frequency. Okay, so what do we see here? This is more complicated. What you see here in broad strokes is a transient period. That's maybe the first 10 seconds. And then a steady state period. That's roughly the second 10 seconds. So the transient period, right? Things are varying in a complicated way in the transient first 10 seconds. In the steady state period, after 10 seconds, maybe a little bit more, things are varying in a smooth way. So in the steady state region, out here, late times, what do we see? We see small amplitude oscillations. But these oscillate, you release the pendulum from 0.1 radian, but now the oscillations are just a couple of hundredths of a radian in amplitude. So these are really small amplitude oscillations. They're at a high frequency compared to the natural frequency. This is the driving frequency. So the pendulum would naturally swing backwards and forwards like this. We're hitting it with a driving frequency that's going like this, 5 times faster. And the motion that we see is just very small motion of the pendulum about the equilibrium point at the driving frequency. In the transient period, this is complicated motion, but in that transient period, what you see is a few things. You see it depends on both the driving and the natural frequencies. So I can see a natural frequency in here and a driving frequency in here. It dies out with a time constant that's determined by the inverse of that beta. Beta was 0.1 of the natural frequency. The inverse of that, about 10 seconds, is sort of this time scale here. Okay. So that's far from resonance. Let's start walking in the last couple of seconds here. Okay. Let's just run it a couple more times and walk towards resonance, just to show you. If I go to just twice the natural frequency, now we've got much bigger oscillations and late times. These oscillations are still at the driving frequency. In the transient period, there was also the natural frequency. Late times, just the driving frequency. The amplitude of the oscillations are almost 10 times bigger. Now we're closer to resonance, but still a fair way from resonance. And so we see simple oscillations at the driving frequency at large times, about the same amplitude as the amplitude that we've released the pendulum from. If I made this, I promise just one more. Let's go real close to the natural frequency. 1% away from the natural frequency, really on the resonance here. Now we've got oscillations of the pendulum at large times, right? They're at the driving frequency, but it's very close, you see, to the natural frequency, and they're huge, right? These are huge oscillations compared to the initial disturbance or position that we located the pendulum at. So this is close to resonance. Look, I'll end there. We've walked through the damp-driven pendulums. We've looked at a lot of the features you commonly met probably in classical mechanics about the damp-driven pendulum. But this is the foundation that we're laying so that next class we can look at new interesting effects like bifurcation, like chaos that appear in nonlinear differential equations.